Hello dear students, the Renu ma'am. Welcome to this video. In this video we will discuss about basically capillarity, capillary tube and Ascent formula. Okay. So beta, what we will do here, initially I will tell you that we are already doing the chapter 11 thermal properties. We are already doing chapter 10 mechanical properties of fluids. Okay, after we will do thermal properties. So baat mein jayega beta. So here capillarity, when we talk about capillarity, is basically the rise or fall of a liquid inside a narrow tube with respect to its surroundings. So simply, if I am saying that I am having liquid here in this container and I just put a capillary tube here and the liquid will rise. Okay, so when the liquid will rise or the liquid will fall. The phenomena of rise of a liquid or fall of a liquid in comparison to its surrounding is known to be capillarity. That phenomena is known to be capillarity. Okay, basically what will we do here? We are having a lot of examples of daily life of capillary action. You are aware that the fountain pan has nib and the nib is broken in between. Okay, the in between portion just behave like a capillary tube. And what is capillary tube? Capillarity, I have told you that phenomena of rise or fall of a liquid in comparison to the surroundings. Capillary tube, beta G, it is a tube of very fine bore. Okay, very fine bore. That means hair-like bore. It is just small in size. The diameter is just like a diameter of the tube is just like the size, or you can say that the size of a hair. So a tube of very fine bore is known to be capillary tube. When we talk about capillarity action, I just told you that in capillary action we will say that the nib of, for example, the nib of the fountain pan, the tip or nib basically is broken in between, and that act as a capillary tube, and due to which the ink will rise up. Okay. In the similar manner, in another example, we can say that if I split, if some ink is just fall on the floor and I just put a blotting paper there, okay, so the blotting paper will absorb all the ink. That means the fine pores present in the blotting paper will behave like capillary tube. Simply, we use towels with towels of coarse cloth. Why? Because they are having many threads, and these threads behave like capillary tube, and again capillary action is there. We are aware that we give water to the roots of the plant, but the water is each and every portion, each and every branch or stem or leaf. So there also capillary action takes place. So we are having a lot number of examples of capillary action. Okay. So here in Ascent formula, capillarity, capillary action, capillary tube. Okay. So these are important segment of this chapter. Now we will do Ascent formula. Okay. Just a second. Yeah. When we talk about Ascent formula, beta G, in that case, what do we do? Simply, just a second. This formula is basically used to find out the height attained by a liquid in a tube, in capillary tube. Ascent formula. Okay, this is basically the formula which help us to find out the height of the liquid rises in a capillary tube. Suppose beta G, we are having a container, okay, in which liquid is there. I am just saying that the liquid where the walls of the capillary tube. In that case, simply I am just putting a capillary tube here. It's a more bad beta. So sorry. So yeah, now it's so the liquid rises up. As the liquid wet the walls of this capillary tube, okay, I am having this capillary tube here, I am just putting it here. So because the liquid rises up and the shape is concave, okay, the shape concave simply means that the pressure here is more as compared to pressure down this shape. So put that this point B A and it is B. If I am saying that the pressure at point A, here the pressure is beta PA. Then here at point B, here at point B the pressure is how much? PA, it will be PA minus 2 sigma by R. Okay, that means A is having more pressure as compared to point B, and that pressure, the difference is 2 sigma by r, where we are aware that this sigma is surface tension. Okay, and this r is the bit of radius of this concave shape. If I draw it completely, it will become a perfect sphere. Okay, when I just draw a large view of this, I will be able to find out the height attained by the liquid. Just a second, please. Yes, sir. So here the excess pressure is more at this point A. Okay, and that pressure is more is basically 2 sigma by r. Sigma is the surface tension, r is this radius of this concave shaped sphere. Okay, when I just draw a large view of this, I will get, I'm just having this bit of, just a sec. And here the height is, just a sec, height is bit of h. Okay, simply we can also say that here the pressure is Pa. Okay, at here the pressure is Pa. Okay, so here the pressure will be more. Here you will get, here Pa is more and here the pressure is less, that is Pa minus 2 sigma by r. Okay, so here in the surrounding everywhere, as we are aware that atmospheric pressure is there. Okay, so beta G here, this like this. So I'm just going to plot it. But this small r is the radius of the this narrow capillary tube. Okay, small r is the radius of the capillary tube. When I draw it perfectly, the complete sphere, then I will get that here this. So it should be like. So sorry, because it will be like this. Okay, this r is the radius of this concave shaped sphere, and just join this O. Suppose this point is K, it is L. Okay. Now here, this theta is the angle of contact. Theta is the angle of contact. This is theta, that's why it should be also be theta. Why? Because it is the radius of this narrow bone. This capillary tube is having radius small r. Okay, theta is the angle of contact. It is completely 90 degree. As it is 90 degree, and we are aware that tangent to this shape is obviously perpendicular to this. That means this is 90, this is also 90. So it is theta angle. So it should be theta here also. Okay. So I wish you understood. R is equal to radius of capillary tube, and capital R is radius of this spherical surface. Okay, now what will we do here? This excess pressure results is basically equal to the rho is the density of the liquid. Rho here is density of liquid. So I will say that this P is equal to 2 sigma by R is equal to rho G H. Why? Because this extra pressure is basically enhancing the height of the liquid, and the shape is concave. That simply means that here the water, as this is made up of glass, and I am just saying that water is capped here. So in the capillary tube the water will rise up, and water wet the walls of the container made up of the glass. So this excess pressure is equal to 2 sigma by r, which is present here. Excess pressure A, P A is greater than pressure at B. Okay, so 2 sigma by r is equal to rho G H. Rho is the density of the liquid, G is the action due to gravity, and H is height. Now I am going to find out the expression of this H. H will give me the value of the height attained by the liquid in this capillary tube. Okay, and what is the purpose of drawing this beta? From this I will be able to find out the value of this capital R. As it is a theta, we are aware that cos theta, from this figure we can say that cos theta is equal to, it is theta, it is base, it is perpendicular. But a cos theta is equal to base upon hypotenuse. That's why I will say that it is smaller upon capital R. From this I will be able to get the value of this R, and this R is equal to r upon cos theta. This r will come with this side and cos theta will go in denominator here. So we will say that capital R is equal to smaller by cos theta. Why I am just solving it? Because I have to substitute the value of capital R here. So beta g and with rho gh is equal to 2 sigma by r. H is equal to 2 sigma by rho g r. This rho and g is numerator here. So equal to sign is there. So it will come here in denominator. H is equal to 2 sigma by rho g. Substitute the value of this capital R. The value of capital R is beta r by cos theta. Here you can see it is r by cos theta. So I will substitute here r by cos theta. So again I am having the formula H is equal to 2 sigma cos theta by rho g r. This is the Ascent formula. Simply the height attained by a liquid in a capillary tube. Okay. So here this is this expression while we are having a very fine bore capillary tube. Suppose you are having a tube capillary tube and the dimension is more, that means this is very broader. In the case of broader, if capillary tube is broader, beta g broader, so we will just substitute the formula 2 sigma cos theta by rho g r minus r by 3. So this term will be here. Minus r by 3 is also introduced. Okay, I wish you understood the chapter. In next class we will solve few numericals, and after we will go for thermal properties of matter. Till then, bye.